In this video, I'll be showing you 5 examples of finding the complete rotation matrix from the base frame to the end effector frame for a 3 degree of freedom manipulator. We'll be using the 5 standard manipulator types that we learned about in a previous video. Here, I'm showing you the kinematic diagram for the Cartesian manipulator. We want to find the rotation matrix R03. That is the rotation of the 3 frame in the 0 frame. We know that we can find this rotation matrix by finding each of the individual rotation matrices R01, R12, and R23, and then multiplying them together. Let's start by finding R01. Each of these rotation matrices has 2 parts. The first part represents the rotation between frame 0 and frame 1 when the joint variable is 0. In other words, the way the manipulator appears in the kinematic diagram. So I need to figure out what rotation is showing here between the 0 frame and the 1 frame. There are 2 ways to do this. The first way is to figure out some combination of rotations that will get the 0 frame to match the 1 frame. For example, if I rotate the 0 frame around its own z-axis 90 degrees, that will make the x0 axis point up, the same way that the x1 axis is pointing up. Then I could rotate around the new x0 axis 90 degrees to get z0 pointing into the page in the same way that z1 is pointing into the page. I could then go and get the standard rotation matrices for a rotation around z and the standard rotation matrix for a rotation around x, plug in 90 degrees to both of them, and multiply them together. But there's also a shortcut way to do this. The shortcut way is using what we know about the meaning of a rotation matrix as the projection of the rotated frame on the original frame. I'll show you an example of what I mean here. Right now, the x-axis of the 1 frame is in the same direction as the y-axis of the 0 frame. In other words, the projection of x1 on y0 is 1. I can write that into my rotation matrix in the first column, since the first column represents the projection of x1. Then I put the 1 in the second row. This means that the projection of x1 on y0 is 1. Since x1 is perpendicular to x0 and z0, I get zeros in the other places in this first column. Next, I can see that the y1 axis is in the same direction as the z0 axis. That means that the projection of y1 on z0 is 1. So in my rotation matrix, I find the entry that means the projection of y1, the second column, on z0, the third row, and I put a 1 there. Since y1 is perpendicular to x0 and y0, I can fill in zeros in those places in the matrix. Finally, the axis z1 is in the same direction as x0. In other words, the projection of z1 on x0 is 1. So in my matrix, I find the place that represents the projection of z1, the third column, on x0, the first row, and I put a 1 there. Since z1 is perpendicular to z0 and y0, I get zeros in the other positions. This finishes the part of my rotation matrix that tells me how the frame 1 is rotated relative to frame 0 when the joint variable is 0. The next part that I need for this rotation matrix is a matrix that represents the rotation due to the joint variable. In other words, what happens to these projections as the joint variable moves? Now, in this kinematic diagram, the joint is a prismatic joint. That means that no matter how this prismatic joint moves, it will not cause any rotation at all between frame 0 and frame 1. Remember that we have a matrix that means no rotation. That matrix is the identity matrix. So the second part of this rotation matrix is the identity matrix. If I then multiply these two matrices together, I get the following result. If you don't remember how to multiply matrices together, I refer you to the video in the section on a review of linear algebra, and I'll show you in one of those videos how to multiply matrices together. For now, I'm going to assume that you already know how to do this. Okay, we're finished with the rotation matrix between 0 and 1. Let's now do the rotation matrix between 1 and 2. We start out this rotation matrix with a matrix that represents the rotation between frame 1 and frame 2 at the time when the joint variables are all 0. We can use the shortcut method to do this. x2 is in the same direction as y1. That means that the projection of x2, the first column, on y1, the second row, is 1. So I'll put a 1 at this position in the matrix. Since x2 is perpendicular to both x1 and z1, we get zeros in those positions of the matrix. Next, y2 is in the opposite direction of z1. That means that the projection of y2 on z1 will be -1. So I'll find the position in the matrix that represents the projection of y2 on z1 and put a -1 in that position. Since y2 is perpendicular both to x1 and y1, those positions get zeros. Finally, z2 is in the opposite direction as x1. That means that the projection of z2 on x1 is -1. I'll find the third column, which represents the projection of z2, and the first row, which represents the projection on x1, and I'll put a -1 in that position. Since z2 is perpendicular to z1 and y1, we get zeros in that position of the matrix. Once again, since there is no rotation due to the joint variable, which is a prismatic joint, the second part of this matrix is again going to be the identity matrix, which means no rotation. The identity matrix is the matrix form of the number 1. So anytime we multiply a matrix by the identity matrix, the matrix doesn't change. So when I multiply these two matrices together, the result is like this. And I'm finished with the matrix R12. Let's move on to R23. We'll start with the part of the matrix that represents the rotation between frame 2 and frame 3 before the joint variable has moved at all. Here, there is no rotation at all between frame 2 and frame 3 before the joint variable has moved. So this part of the matrix will be the identity matrix. Next, we do the part of the matrix that represents the rotation due to the joint variable. Since this joint is also a prismatic joint, there is no rotation due to this joint. So this part of the matrix is also the identity matrix. So when we multiply these two matrices together, what we get is also the identity matrix. It's like multiplying 1 times 1. You'll still get 1 out in the end. Now that we've found the three rotation matrices R01, R12, and R23, we're done with this example. We could do another step here where we multiply these three matrices together, but typically we'd stop at this point and put these matrices into our code, so I'll stop here in the example as well. We'll move on now to a new example. Here's an example that will be much more interesting than the last one. This is the articulated manipulator. In general, the more revolute axes we have, the more interesting or complicated the rotation matrices will be. Once again, what we're trying to find is R03, the rotation of the end effector in the base frame. And we know that we can find that by multiplying together R01, R12, and R23. So we want to find each of these individual rotation matrices. Let's start with R01. The first part of the matrix is the part that represents the rotation of frame 1 relative to frame 0 before the joint has moved. We can use the shortcut method to do this. x1 is in the same direction as x0. In other words, the projection of x1 on x0 is 1. So I find the position of this matrix that represents the projection of x1 on x0, and I put a 1 in that position. Since x1 is perpendicular to y0 and z0, I put zeros in those positions. Next, y1 is in the same direction as z0. That means that the projection of y1 on z0 is 1. So I find the position that represents the projection of y1 on z0 and put a 1. Since y1 is perpendicular to x0 and y0, we get zeros in those positions. Finally, z1 is in the same direction as negative y0. So the projection of z1 on y0 is negative 1. I put a negative 1 in the position that represents the projection of z1 on y0. Since z1 is perpendicular to z0 and x0, those two positions get zeros. And we're done with the first part of this matrix. The second part of the matrix is the part that represents the rotation due to or because of the joint variable. Now we have to be careful here about which axis we say the rotation is around due to the joint variable theta 1. Theta 1 is a rotation around z0, but it's also a rotation around y1. So which rotation matrix should we use? The z form of the matrix or the y form of the matrix? The answer is we could use either one, but it matters where we place the matrix depending upon which we use. If we want to say that the rotation is around the z0 axis, we have to put the z matrix here before the part of the matrix we already have. If we want to say that the rotation is around the y1 axis, we can do that also. We'll take the y matrix and put it here after this matrix that we already have. We can do it either way. In this example, I'm going to use the y rotation and put it on the right. I'll use both of these methods in some of these examples so you can see both ways that it can be done. So I'm going to go get the standard form of the y rotation and plug in theta 1. When I multiply these two matrices together, I get the following. I'm going to start using just the letter C to represent the cosine and just the letter S to represent the sine. That will simplify the written equations. So here we have the final R01 matrix. This matrix is telling us that the y1 axis is always projected exactly onto the z0 axis. We can see that this is true. No matter how theta 1 turns, y1 is always in the same direction as z0. We can use things like this as a little bit of a gut check to see if the results we get make sense with what is physically happening in our manipulator. Let's move on to R12. We first write out the matrix that tells us how frame 2 is rotated relative to frame 1 when the joint variable theta 2 is 0. We can see that these two frames are right now in the same orientation. That means that this part of the matrix will be the identity matrix, no rotation. Next, we need a matrix that tells us the rotation due to the joint variable. Theta 2 is a rotation around the z-axis. In fact, it's a rotation around both z1 and it's a rotation around z2. That means that it doesn't matter whether we multiply the matrix on the right or on the left. We'll get the same answer either way. So we'll go get the standard form of the rotation matrix around the z-axis and plug in the joint variable theta 2 here. Now, because we're multiplying by the identity matrix, the other matrix is not going to change. The final rotation matrix 1, 2 is the same as the part of the matrix that is due to the joint variable. Okay, we're done with the rotation matrix from 1 to 2. Now, on to the R23 matrix. Frames 2 and 3 are exactly the same right now when joint variable theta 3 is 0. So this part of the matrix is the identity matrix. Next, we have to get the part of the matrix for the rotation due to the joint variable. This is a rotation around Z2 or around Z3. It would be the same. So once again, I can either right multiply or left multiply this matrix. I'm just going to put it on the right since that's a little bit easier to write. I plug in the joint variable theta 3. I then multiply these two matrices together to get my complete R23 matrix. Now that I've found R01, R12, and R23, I'm done with the rotation matrices for this kinematic diagram. I could now go put these three matrices into my Python code as I showed in the last video. So we'll move on to the next example. This next example is the spherical manipulator. Now I need to give you a little reminder about what happened when we were drawing this kinematic diagram. Remember that we had to move the location of frame 2 back to be located on top of this second joint in order to follow Rule 3 of the rules for assigning frames to kinematic diagrams. So the purple frame 2 in this picture is the correct frame 2. The red one was the one we drew initially. We'll be using the purple frame 2 from now on for deriving our rotation matrix and also for doing our displacement vector in the next videos. Let's start by finding R01. We'll first do the part of the matrix that represents how frame 1 is rotated relative to frame 0 now before theta 1 has moved at all. x1 is in the same direction as x0. So the projection of x1 on x0 is 1. Since x1 is perpendicular to y0 and z0, those numbers will be 0. y1 is in the same direction as z0. So the projection of y1 on z0 is 1. And it's perpendicular to the other axes. z1 is in the same direction as negative y0. So the projection of z1 on y0 is negative 1. And the other elements are 0. Now we have to write the part of the rotation matrix that is due to the joint variable. Theta 1 is a rotation around z0, or it's a rotation around y1. So we have to either go get the standard form of the rotation matrix around y or the rotation matrix around z. If we want to use the rotation matrix around z, it has to go on the left. And if we use the rotation around y, it has to go on the right. Since last time we encountered this, I got the y matrix and multiplied on the right. This time I'll do it the other way around. I'll go get the z matrix and multiply it on the left. When I multiply these two matrices together, I get the following. If you go back in the video to the last time we made this decision and we put the y matrix on the right, you'll see that the answer that we got is exactly the same now as what we got last time when we did y on the right. We'll move on now to R12. Remember that here we're comparing the 1 frame in red to the 2 frame in purple. We'll start out by writing the part of this matrix that tells us how frame 2 is rotated relative to frame 1 right now. X2 is in the same direction as Y1. Y2 is in the same direction as Z1. And Z2 is in the same direction as X1. Now, the rotation theta 2 is around Z1, or it's around the axis Y2. So again, we can either left multiply by Z, or we can right multiply by Y. This time, I'll right multiply by Y. I go and get the standard form of a rotation matrix around Y, and I plug in the variable theta 2. I then multiply these matrices together. And that is the complete R12. Let's do R23. Frame 3 is in exactly the same orientation as frame 2. That means that the first part of the rotation matrix will be the identity matrix. Also, the third joint is a prismatic joint, and prismatic joints do not give us any rotation due to the joint variable. That means that the second part of this rotation matrix is also the identity matrix. When I multiply the identity matrix by the identity matrix, what I get out is again the identity matrix. So this is my complete R23, and I'm done with this example. Here's our last example, the cylindrical manipulator. We'll start with the part of the rotation matrix that tells us how frame 1 is rotated relative to frame 0, not due to theta 1. These two frames are in the same orientation right now, so this part of the matrix is the identity matrix. Next, we need the part of the rotation matrix that is due to theta 1. Theta 1 is a rotation either around Z0 or around Z1. In both cases, it's a rotation around Z, so I can either left multiply or right multiply by the Z rotation matrix. I'll put it on the right just because I have more room to write there. When I multiply by the identity matrix, the other matrix doesn't change, just as if I were multiplying by 1. and I'm done with R01. On to R12. We start with the part of the matrix that tells me how frame 2 is rotated relative to frame 1 right now. X2 is in the same direction as Y1. Y2 is in the same direction as Z1. And Z2 is in the same direction as X1. Now, the next part of this matrix is the rotation that is for the joint variable. But since I have a prismatic joint, there will be no rotation due to the joint variable. So I need to multiply this matrix by the identity matrix. But I know that any time I multiply a matrix times the identity matrix, the matrix doesn't change. So I'm actually finished already with R12, and I'll go ahead and stop here. Now let's do the rotation R23. I'll first do the part of the matrix that tells me how frame 3 is rotated relative to frame 2 right now. These two frames are rotated exactly the same way right now, so that part of the matrix is the identity matrix. Also, this joint is a prismatic joint, so there's no rotation due to the joint variable either. That means that I'm actually done with R23 also. We've now seen a bunch of examples of finding the rotation matrices for different kinds of manipulators. The rotation matrices tell us how the end effector is rotated or oriented relative to the base frame. We know that rotation is not the only way that the end effector can change. It can also change its position. In the next videos, we'll be looking at how the end effector changes its position as the joint variables change their values.